Hello, and welcome to Lecture 2 of Magnetic Interactions in Phys 1204. So far, I've mostly been talking about permanent magnets, things like rare earth magnets and compasses that we're fairly familiar with. But those permanent magnets actually turn out to be extremely complicated. What's easier to understand is the magnetic fields that are produced by currents in wires. So here is a wire, and the current in this wire is running upward, like so. And if you look, you can see that the magnetic field is that way in front of it, and this way over on this side, and this way over on this side. We say that the magnetic field due to a wire follows a right-hand rule. And here's what's meant by that. If you wrap your fingers of your right hand around the wire so that your thumb points in the direction of the current, then the way your fingers wrap around is in the direction that the magnetic field points, right? Over here this way, in front this way, over here this way, and behind the wire it would point this way. The way the compass needle responds to the current in the wire shows us that moving charges, or in other words current, generate magnetic fields. And those magnetic fields, due to a straight wire, are concentric circles which are centered on the wire. And the direction that the field points around the wire is determined by a right-hand rule. We're going to encounter several right-hand rules, so we'd better be specific. This one is called the right-hand rule for fields due to currents, or more briefly, just the right-hand current rule. And so the figure, or the picture that I've annotated, shows how it plays out for this particular case, or here's a cleaner schematic view. You might also like to picture it with the wire perpendicular to the screen and the current coming out of the screen at you, in which case the field lines would be these circles. And you should practice applying the right-hand rule. I find students have a great deal of difficulty figuring out how to orient their hands. In this case, you would put your thumb towards you out of the screen so that it matches the figure, and curl your fingers. Your hand would look something like this. And so your fingers are showing you which way the field curls around the wire. And you can also draw it as field vectors instead of field lines. Note that I'm now indicating magnitude. We still don't have a way to define the magnitude of the B field. We'll get there. But as you might imagine, the magnetic field is strong nearer the wire and weak farther away. Like I say, students seem to, initially at least, have a great deal of difficulty with right-hand rule, and part of it is that you just often have to sort of contort your arm to be able to stick your thumb in the right direction. So try this out. Here's a wire in the plane of the screen, and we don't know which way the current is going in it. But we've measured the magnetic field, and as shown in the picture, remember dots are vectors out of the page and x's are vectors into the page, the field is coming out of the plane of the page to the right of the wire and into the page to the left of the wire. And so from that information, figure out the direction that the current is running in the wire.